So let's now restart our model analysis. So next step, as I told you, is to constrain the model. So why do we need to constrain the model? Why do you think we need to constrain the model, anybody? Because the model needs to be in equilibrium. If you don't put constraint on the model, when you apply the force, the model will start moving, isn't it? And because we are carrying out a static analysis, it will not be able to solve it. So just like in a real problem that you solve in this course, you always assume a certain boundary condition on one of the ends, right? So in the same way, the software needs to know what the boundary condition is. So in this case, I will apply the boundary condition on this edge, and I will basically, I can just simply select this face, and then I can go on to the fixtures and right click and say fixed geometry. Now there are so many different options here. You can choose slider types, you can choose elastic support, and other types of the boundary conditions. But in our case, we are saying that our part is completely fixed from one side. So that's why we are using fixed geometry as the option. So internally, what it does is it says that the value of all the displacements, meaning all the u variable basically, is equal to 0 on this face. Now the question is, should I only select the face or should I also select the edges? In this particular problem, it will not make any difference whether you select edges along with the face or not. But depending on the problem, it may be important to make sure that edges are also selected. Especially, for example, later on, if you wanted to apply a shearing load on this case, in those cases, the edges may actually be important to constrain. A few weeks later, we will be doing another example of a torsional cylinder, and in that, I will show you some other boundary conditions that need to be applied as well, and not just the fixed end condition. But for today, it's only the fixed end condition, and what you'll need to do is you can just say OK, and that's it. So this will now fully constrain the model from moving in along the x-axis. Okay, so that's what we have done. Next step is to apply the load. To apply the load, we go on to the external load tab and we click on the force. Again, I'll go back, I think I did it too quickly. So we go on to the external loads, and you can see here there are so many different options of the loads. Depending on your actual problem, you will need to apply different types of load. So for example, if you are analyzing a pressure vessel, you will apply a pressure type of load. If you are analyzing a shaft that is experiencing or transmitting torque, will become the type of the load. If you want to include the weight of your member in your analysis, then you will be applying gravity as part of the loading as well. But right now, we are just assuming that the weight of the member itself is not important, and all we are doing is applying an axial force. So in this case, the axial force is on the end opposite to the fixed end, which is this face. Now, you notice here that the direction of the force vector is actually inwards. So it is basically causing compression. So that's not what we need. So you'll go here and you'll click on reverse direction option, and that will then basically apply the load on in a tensile manner. So the direction of these arrows will depend on the orientation of the force and how the part was generated. If you have generated parts slightly differently, you may not need to reverse the direction. But in my case, I will need to reverse the direction. Then is the magnitude of the load. Because we are using the SI system, therefore the magnitude of the load will be in newtons, which is 26,650 newtons. Let me reconfirm that from our slides. So yes, we solved this problem for 26,650 newtons of force. Another important option underneath here is whether you are trying to apply the load per item, or are you specifying the total magnitude of the load. And in this particular case, it will not make any difference because you are only applying the load on one face. There can be many other cases where you have multiple faces and multiple regions on which you are applying the load, and then you have to decide whether you will apply per item or total. So with that, I will accept the load that is being applied, and I will just say OK. So that means another important part of our modeling is complete. We have applied them, defined the material, we have fixed the model in the boundaries, we have applied the load. But the software still cannot actually solve this problem because we have not defined what we call as the mesh. Because mesh is basically what allows the software to discretize the region and then basically define the finite element equations at each of those nodes and then solve the problem. So that is the most important step, and I'll do that in the next step now. So to apply the mesh, we will have to go to the mesh tool. In the mesh tool, we right click on this and we say create mesh. So when we create mesh, you are given this option of a dialog box. Again, depending on the software version, I think this can be slightly different, especially in the book notes. There are some changes. But you can see right now this slider is here in the middle. This middle position is basically called as the default position. If you move the slider, you can always bring it back to the default position by clicking on reset, and it will come back to its original position. So basically what this slider is doing, if you look underneath, so if you go onto the mesh parameters and select standard mesh, so there are different types of meshes that you can define. Because this is your first finite element analysis, I'm not going to go into details of the rest of the other types, and I will just simply use a standard mesh. And in this case, if you move the slider, you can see that these numbers here are changing, which means that these dimensions related to the elements in which it is going to divide your part is going to change. If you move it towards the fine, this number becomes smaller, meaning your element size is becoming smaller. If you move it towards coarse, this number is becoming bigger, meaning your element size is becoming bigger. Again, I'll just go back and set it to the default size. The default size gives you an element edge length for this part based around 4.27. Keep this in mind, this is not universal and it depends on your part geometry as well as the features that you will have. So right now we will use this standard definition with the default size. That's why in the analysis name we called it as draft mesh. Default size. The draft mesh part of it can be seen by going on to mesh quality tab. So if you click on the mesh quality tab, you have two options. One is the high option and the other one is the draft option. Right now, I will just move this to the draft option. We normally use draft analysis if we are not really looking for very accurate stresses around the features such as notches and other small features. And let's say we have a very big and complicated part and we are just trying to get an initial idea of the stresses. That will still be comparable to your hand calculation results, right? But it may not be purely, it may not be very accurate, okay? So let's look into this and look into the effect of this. So we'll say OK to apply this changings. And as soon as I say OK, you can see now the software has generated this mesh on it. Basically, what it is doing is now it is treating each one of these triangles as a separate entity. And you can see that all of these triangles are connected at those nodal points. So remember in the class, I gave you that example with the circle and how to find the value of pi using those line segments. So it is analogous to that. But right now, instead of just the geometry, it also has got the information about the material properties at each point. And it can then solve those equilibrium equations at each of these points as well as the constitutive equations. Anyways, let's now try to analyze this problem. I'll actually do that in the next step. Before I move on to the next step, I want you to note down a few parameters, and those parameters are basically related to your mesh size. So if you click on the back on the main mesh tab and then right click and then you go on to the details, you can see all the details about your mesh. for me, what is most important right now is the number of the elements as well as the total number of nodes. Okay, there are other important aspects as well, but right now I'm focusing on these aspects. So basically, total elements is 6,444, and the nodes is 1,606. So what I will do is I will open an Excel file, and I will start recording the data for this. To speed up things, what I have done is I will open an existing file that I did with the other section yesterday. I'll copy this over this sheet so that this is now for your section. Okay. Okay. And I will remove all the data that is there apart from the one that we will be doing now. So, okay. So you can see here I have written here for the standard mesh quality, right? You have got the element number is 6,444 and the number of nodes is 1,606. So this is the information that I want all of you to record for each of your models. Okay. Let's now go back to the analysis, and we will now actually start plotting the result. But let me just stop the recording at this point. I will basically continue in the next segment.